This is continuing on with the dot product, section 2.9, and now we're going to talk about the projection of one vector onto another vector. We've already done a little bit of this when we dealt with f prime. So if we recall, if we talked about f prime, it's going to be the projection of that 100-pound force onto the xy plane. And kind of a way to visualize that is if there was imagine that this was a solid rod. I'm going to draw this as a stick or a rod that's kind of sticking up in this kind of arrangement. And if you had a flashlight and you were going to shine it straight down, I'm going to try to draw a little flashlight here. I don't know if that's a good way of doing it, but if you drew it straight, if you held the flashlight, if you held that rod in that position and shined a flashlight coming straight down, you might imagine that there would be a shadow that would be cast in that sort of on that plane in that way. And so anyway, that's what the projection is. It's the shadow of the force onto another line or plane. Okay, and so we can use it to find that projection onto a plane or onto an axis. For example, we've already done this as well. We didn't call it dot product, but basically we said if there's a force, and if we want to find out the component on the x-axis, which would be the projection onto the x-axis, it is really just the cosine component. The same thing here on the y-axis. It's actually going to be going in this direction, but that's going to be the component onto the y-axis, which is the cosine. All right, so let's use those rules and that understanding to solve a couple of little problems. So when we're finding projection, in this case, the magnitude of the force does matter. So the projection is the magnitude of that force when viewed perpendicular to the other vector, or the shadow that might be cast. So in this case, the magnitude of the force does matter. So we need a vector description of the forces, and we need to find the vector onto which the shadow is cast, or onto which the force is aligned. So imagine this little Pinewood Derby car here. I've got some x, y, z axes defined for us, and let's say that it's constrained to move only in this direction. And you can imagine that because of the wheels, it will only logically go in one direction. If you pulled straight up, and I'm going to try to imagine that you're pulling straight up on this, you could probably guess the thing doesn't move. Or if you pulled perpendicular in the horizontal direction, you pulled perpendicular to that 30 degrees, it probably wouldn't move. However, if you had any component of the force going along the line of motion, then it would probably move along that line. So let's find out what that magnitude of the force on that line might be. So here's our process. We're going to use the A dot B. We're going to look at the magnitude in the x component, or in the x direction, and the magnitude in the x direction of the other vector, and multiply them together and then add the three pieces. It's also going to be the cosine of the angle. In other words, if you could find the cosine of the 3D vector, then you could do it that way. So there are two methods. If you knew what the magnitudes were, you could use the cosine. If you don't know what the magnitudes are, then you have to find those magnitudes and do that. So here's what we're going to do is we're going to dot one product onto the unit vector of the direction that we're going to go. All right, so the first thing let's find the unit vector of the unit vector of that vector, which is our direction. So we'll call this unit vector of B. So what is the unit vector of B? Let's put that back down here. Well, it looks like it's on the xy plane, so there's going to be a cosine component in the I direction and a sine component in the j direction. So it's pretty easy to see that. Unit vector is going to be cosine 30 I plus sine 30 j. Now, maybe we have a force. I didn't give that force, but let's just call that force. Let's call it 10I plus 10J plus 10K. In other words, it's a three-dimensional force. It's got a vector description. And to find out the projection onto that line, you just multiply the two together. So I'm going to say F dot unit vector of B is going to be equal to 10 in the I direction times the I direction here, or the I component, cos 30, plus 10 in the J direction times the sine of 30. And there is no K component of the unit vector, so we just don't have to worry about that one. So that's going to be whatever it is. Actually, I didn't even multiply that out. So you can multiply that out and find out what the answer would be. But that would be the component of that force that's going in the direction of motion of our little Pinewood Derby car. Okay, so let's continue on and look at this textbook problem and see if we can find out. What we're going to do here is we are trying to find the projection of this force onto this line. Okay, 56 newtons goes from A to D, and the line that we're looking at is AO. So what we want is a vector description of that force and the unit vector of AO, and then we're going to dot them together. So let's get started with AD. So F AD is, we can see that it is 56 newtons. And let's look at the unit vector. We are going, let me put it in blue here. I'm going to say that from A to D, we're going to go that far in the I direction, which is 1.5. Go this way in the J direction, so that'd be -3, and then up to D, which would be +1. So that's going to be 1.5I minus 3J plus 1K, and divide that by the square root of the sum of the squares. Okay, and that gives us a vector description, or a Cartesian description of that force. Okay, now we have FAD defined. How about AO? So I'm going to look at the unit vector of AO, and here I'm going to go from here, going to do the same thing, but now I'm going to go down instead of up from AO. So let's go ahead and put that there. Of the square root of the sum of the squares. And again, I'll sometimes shortcut the square root of the sum of the squares since we're getting pretty familiar with that. But this is the sum, this is the squares, and all I'm looking for is the square root of the sum of the squares of those two components, or those three components. And so let's write the vector description of that. .429I minus 0.857J minus 0.286 K. Okay, now I have the unit vectors, and all we're going to do to find out that projection is just multiply the x components, the y components, the z components, and then add them together. So I'm going to say F dot the unit vector of AO, and these are both vectors. It's going to be equal to 24 times 0.429 plus -48 times -0.857 plus 16 times -0.286, and that's going to be equal to looks like that is equal to 46.9 newtons, and that's equal to the projection. Okay? Alright, let's see what you guys can do. Let's look at this and pause the video and go ahead and try to find out what the projection of F1 is. Oops, didn't mean to do that. F1 is onto this line. Now again, remember the magnitude of that force there does not matter. However, the magnitude of this force does matter. You can see there's an angle between them. You may want to solve for that angle. You don't need to. But find the vector description of this force. Find the unit vector of that line. Dot them together, and we'll find out what the projection is onto that line AC. Okay, here is the solution. And what we're looking for again is finding the projection of this onto that line. So here's the vector description of F1. 70, I've got my distances, I've got the magnitude under there, and there's the vector description. I've got the unit vector of this. In other words, I look at the distances and I find out the magnitude and multiply those together. So now I have a magnitude of the components of this, the components of that unit vector, and we just dot them together by doing the arithmetic multiplication. So I've got that component times this, the 70. Well, actually here I got it right here. I didn't even see that there. So anyway, so I got 20 times negative 0.525 times negative 0.549, 60 times this one, 30 times this one, and you add it together and you get the projection. Alright, last thing I want to just visit with you about is in preparation for exams and also for your studying. There are some formulas that are in the back of the book, and I've added a couple things here to this formula sheet, and I just want to point this out to you as we go through this. But you should be familiar with these formulas which are in the back of the book. These are kind of the fundamental formulas of statics, as it says, fundamental equations. And we'll be using some of these things as we go through the course, but this sheet will be provided to you on exams. Also has just a little reminder of some cosine law, the sine law. We just got done talking about the dot product, and there is the generic descriptions, and we may also find that the projection onto another vector using that description might be helpful. The second thing that will be provided to you is this little review that I put together of the components of the forces in both 2D and 3D, and so we've already talked a little bit about this part of it. And then this down here is just a little review of how you can describe forces in 2 dimensions and 3 dimensions, and basically it moves into the unit vector. So in other words, if you have a force of 100 and it moves some distances, this is a good Cartesian description. This is also a good description, and this is a good description. Remember that you don't want to forget dividing by the square root of the sum of the squares. Again, every semester we get a number of students that try to describe the force like that, which is incorrect. And then the same thing with 3 dimensions. So anyway, this is an example of what you might incur, or what these are just an example of some forces. Obviously, this isn't the only way of describing things, but don't forget the square root of the sum of the squares. It is not equal to that. Anyway, this will be provided for you or provided to you on the exams.